Hello, welcome to Fundamentals of Acoustics. Today is the start of the last week of this course, that is the 12th week, and over this week we will cover a couple of topics. The first important topic which we are going to cover is octave band analysis, and this is a technique which is very frequently used to represent data on noise in the industry. So, that is one thing we plan to talk about. The second theme would be reverb time or reverberation time. And finally, we will talk about a couple of additional terminologies, specifically STC, that is the sound transmission coefficient, and NRC, which is the noise reduction coefficient. And both these terminologies are very frequently used in contexts and situations where the intent is to reduce noise getting transmitted from point A to point B. So, those are some of the important themes for this week's discussion, and we will start our discussion by talking about octave band analysis. Okay. So, first thing we would like to know is what do we plan to do in this analysis, what do we do? So, consider a noise source. Let us say there is an engine in a room and it is generating some noise. So, if I record its signal in time, so this is time axis and this is pressure as a function of time, then the noise signal may look something like this, like that, some noise signal, right. Now, if you show this noise signal to industry experts, they will not make it does not make a lot of sense because they cannot interpret these data. So, essentially you have a large number of points and each point is a plot of pressure against time. So, what do you make of it? So, a lot of times people in industry and also even the scientific community, they say that from this data which is in time domain, so this is in time domain, please tell us how much sound is being produced in specific bands. Okay. So, the question is, use pressure in the time domain data to calculate noise levels in specific bands. So, what is a band? Band is a range of frequencies. So, for instance, a person may ask that how much noise is being produced between 100 and 200 hertz. Okay. So, you can say that okay, based on this pressure data you will be expected to calculate how much noise is being produced in 100 to 200 band. So, that will be one number, that will be one number, and here the units will be either dB or it could be even dBA. So, then they will say okay, I want noise level in 100 to 200 hertz band, 200 to 400 hertz band, 400 to 600 hertz band, and so on and so forth, right. So, this may be 400, this may be 600, this may be 800, this may be 1200. So, here I am not following any specific pattern, but the question which may be asked from you from your employer or from the industry is that if I give you data in the time domain, can you tell me in decibels how much noise is there in each specific band? How much sound energy or sound power is there in each specific band? So, between 100 and 200 hertz, how much is the sound power level? Between 200 to 400, between 400 to 600, 600 to 8. So, these type of plots are very frequently used, and people, noise experts, look at these plots and then they figure out that, oh, most of the noise, when they look at this plot, they say most of the noise is in this 800 to 1200 band. So, based on this analysis, then they say that if I have to reduce noise of this engine, I have to make sure that I reduce this type of noise in the beginning, because if I reduce this noise, it will not make much of a difference, because the decibel level of noise in 600 to 800 hertz band is very less. So, if I reduce and even eliminate 600 to 800 hertz band noise, it will not make much difference to the overall noise level. So, based on these type of plots, people figure out strategies to reduce noise in areas or from machines. So, that is one use of these type of plots. The other use of these type of plots is that they can compare. So, let us say there are two engines. So, we have engine 1 and engine 2, and they want to compare how noisy is each of the engine. So, once again, the interest is not only to just look at one single number, but they will make a plot like this for engine 1 and a similar plot like this for engine 2, and then they will compare that, okay, in this particular band 100 to 200 hertz band, engine 1 has more noise, engine 2 has less noise. In 200 to 400 hertz band, engine 2 has more noise, engine 1 has less noise. So, based on these plots, data is interpreted and noise levels for different machines or similar machines are compared. So, then based on that you can make an assessment. This particular machine is better in terms of noise production compared to a machine from some other company or something like that. So, two important uses. One is these plots help us reduce or develop strategies to reduce the noise from machines, and another important use is that these type of plots also help us compare different sources of noise and then rate the different sources of noise in a particular order. So, these types of plots are very frequently used, and this is what, if you are an expert in noise, this is what is expected of you as a noise engineer, to produce plots like these. Now, there is a special type of plots of this type, and they are known as octave band plots. So, this is not a, this plot which I have drawn here, it is not an octave band plot. It is not an octave band plot. Why? Because this is an octave, right? Here the ratio is 2, but the next band, this is also an octave, 200 to 400, but 400 to 600 is not an octave. 600 to 800 is not an octave, 800 to 1200 is not an octave. So, in octave band plots we make similar graphs, but we plot for noise energy for an octave, a band which is 1 octave wide. So, the range of frequencies, upper frequency limit and the lower frequency limit in each band is 2. Okay. So, these are known as octave band plots, and then further, so you can have an octave band plot like this. So, let us say this is 1 hertz, 2 hertz, 4 hertz, 8 hertz, 16 hertz, or let us say 100, 200, 400, 800 and 1600. This is an octave band plot. And then for each band plot you can have different noise levels. Another possible octave band plot could be 125, 250, 500, 1000, 2000. This is another octave band plot, because here also the frequencies at which we are plotting noise are separated by an octave. So, the ratio is 2, but the industry says that I want you to produce these graphs in some, both of them are octave band plots, okay. Both of them are octave band plots, but the industry says that I want you to produce these plots at some specific frequencies, okay, in some specific bands, because a third person can produce another octave band plot and it could be something like this: 300, 600, 1200, 2400, 4800, right. This is also an, if you make plot for these values, it will be an octave band plot. So, amongst all these three situations, A, B and C, the frequencies at which data is being plotted, they are not consistent. So, the industry and experts in acoustics have said that whenever we are going to report data on noise, we are going to report data on some internationally accepted octave bands, okay, so that you can compare apples with apples. Otherwise, one industry or one company will produce data in format C, another company making similar devices will produce in format A, and then you cannot compare those two, okay. So, with that intent, people have developed standard octave bands. Okay. So, once again we will go back to our original goal. What is our original goal? Our original goal is to learn how to do octave band analysis. Okay. This is our original goal. And to do this, we need to know three important things. We need to know three important things. First, we have to know how to calculate dB and dBA from time series data. This is the first thing we have to know. I think we know this to a certain extent, but today we will make it more explicit. The second thing we have to know is understand what are industry standard octave bands. Okay. And the third thing we have to know is how to do forward and inverse discrete Fourier transform. So, if we know these three things, we can combine all this information and learn how to do this octave band analysis. So, what we will do is we will address this question first: how to do forward and inverse DFT, because from there all, because once we do 3, then from 3 we can also do 2, we can also do 1 easily. So, next couple of minutes we will discuss how to do forward and inverse discrete Fourier transform. Okay. This we had already discussed earlier. So, if there is data, so what is forward? Forward DFT? Here we convert data in time domain to frequency domain. Okay. And the relation for this we have discussed earlier. So, I am just going to cite it, but I will not explain it. So, the relation to do this is this thing. So, here the addition is on the index n and it goes to n minus 1. So, once again very quickly I will recap. K is the index on frequency, n is the index on time, and n is number of points. So, if we use this transform, we can calculate xk, capital Xk. So, capital Xk is a string of numbers which represents a time series data in the frequency domain. Okay. Now, I will spend maybe 2 more minutes on this because I am going to introduce one more term. So, let us look at this parameter. What do we see here? Here xn is being multiplied by exponent to the power of I 2 pi kn over n. So, this involves multiplication. Okay, it involves multiplication. For a given value of k, how many times we are going to multiply it? For a given, so for a given value of k, we are going to have n multiplications. Okay. The other thing is, and how many times we will have to compute xk? N. So, there are n values of xk we have to compute. For each value of xk, we have to do n multiplications. So, we have to compute n values of xk. So, total number of multiplications which is required to be done is n times n, or it is the order of n square. Okay. So, the total number of computations which we have to do in the forward DFT is of the order of n square. So, if n is let us say 300,000, sometimes these time data can be very large numbers, or 3 lakh, then it has to be 300,000 times 300,000. So, it is a very large number, so it can take a lot of time. So, this way of doing forward this discrete Fourier transform may not be, so this is mathematically accurate, but it may not be fast enough. So, some people have developed faster methods to do all this computation. So, a special type of DFT is known as FFT, and what is FFT? It is known as fast Fourier transform, and it is not any different from DFT. It is a particular type of FFT, but it is just faster, and in this algorithm the number of computations which have to be done is n log n. Okay, this is to the power of 10. So, this number of computations is significantly smaller, it is significantly smaller. So, this is fast Fourier transform, and there are several algorithms for this. So, one algorithm is Cooley-Turkey, another algorithm is offered by Brun, another algorithm is known as prime factor algorithm, and there are so on and so forth. So, what the point is that in literature you will most of the times, 99% of the times, you will hear this term FFT and you will not hear DFT. So, you may get confused, but please realize that FFT is just a special and a faster version of DFT. So, once you know FFT or DFT, you can convert time data into frequency domain, and then for the inverse transformation, what do we do? The relation is simple, it is very similar. So, xn is data in time domain, and that equals xk e, and earlier we had a negative exponent, here we have positive I 2 pi k n over n, and here we are adding up these terms on which index? K is equal to 0 to n minus 1. So, when I do all the addition, k goes away, I am only and I only end up with xn. So, in the first calculation I compute x0, in the second calculation I compute x1, and so on and so forth till n becomes equal to n minus 1. Okay. So, this gives us, so what does this do? It converts frequency domain data into time domain. Okay. It converts frequency domain data into time domain. This is there. So, the point is that if I have time domain data, I can convert it into frequency domain data, and I can use the same data, or if I want I can modify it and convert it back into time domain data. So, that addresses our first question, how to do forward and inverse transformation. So, the next thing we are going to discuss is understand what are industry standard octave bands. So, once we do these, then we will address the third question. So, our next theme is going to be what are industry standard bands. Okay. And there is actually an international standard for these bands, and it is known as ISO, International Standards Organization, and 266. So, if you want to learn in detail about these industry standard bands, you should refer to this standard ISO 266, and it gives you all the details of the standard. But in this course we will still cover some of the details of this standard, and we will explain how do we arrive at these different bands. So, that discussion we will do tomorrow, because our time for today's lecture is over, and till then have a great day, and we will meet once again tomorrow to discuss industry standard bands. Thank you.